And I think we are online again. Welcome everyone in the stream, in the chat. Welcome, Mr. Kodosky. Very nice that you could join us. We have a very special guest. He's the co-founder from NI. He's the actual inventor of LabVIEW. So he's using LabVIEW since 1986, since LabVIEW 1.0. And yeah, Jeff, hello.
Hello.
Hello. How are you doing?
I'm doing well, thank you.
Good to hear that. Good to hear that. Yes.
It's being at home and doing well. Thanks.
Yes, and you were going to update us on the target structure and the channels. You did a first presentation, I think a year ago or 2 years ago during the CLA summit.
So yeah, I'll get into that in a moment. If I should start now.
Sure, please start.
Just have to mention that it's really strange to be physically isolating during this global pandemic, but using technology to communicate and interact at an unprecedented level. In normal times, I probably wouldn't be able to visit and present at your meeting, but in today's world, distance doesn't matter. In fact, I think we have a unique opportunity to bring the global LabVIEW community together as never before. So I'm particularly thankful to the Dutch LabVIEW user group for inviting me to present today, and I hope this will inspire a new level of collaboration among user groups worldwide. So I thought today that I'd give you an update on the research that I've been doing in the past several years on targets and channels. So let's see. I'm not able to, yeah, okay, there we go. So, my primary focus is on what LabVIEW was uniquely positioned to do to advance the state-of-the-art in systems design. Measurement systems that are designed today are actually distributed. We have a host PC, LabVIEW RT, LabVIEW FPGA, and the future trend is toward even more distribution. We'll have cloud computation, storage, web and mobile UIs, and IoT, and so on. And my view is that distributed systems should be designed and visualized using graphics, because that makes relationships and communications visible and understandable. Now, the tools that we use to build distributed measurement systems add artificial complexity to the inherent complexity of the application we're trying to build. And I think the way to rein in this artificial complexity is by using abstraction. And what I like to think of as semantic zooming, where you zoom in to see details and zoom out to see the big picture. And if you can do that while you're developing, I think that will foster more modularity in our designs and result in more maintainable and extensible systems. So let me start with talking about channels. Now, channels, I believe, are a major advance in the representational capability of LabVIEW. Ever since LabVIEW 1, I've been frustrated by how to represent the communication between concurrently running loops. A decade ago, I began to experiment with a promising approach that was eventually productized as channels in LabVIEW 2016. So it's been out for quite a while already. Channels are very helpful today, but they'll be even more helpful when we can represent distributed concurrent loops. I've described channels multiple times before, so I'm just going to summarize with a simple example. So a channel has a distinctive pipe-like wire pattern, and the lack of visible tunnels at the structure borders indicate that it's a channel rather than a regular wire, and a channel actually implies concurrency rather than scheduling dependence. So people who are familiar with LabVIEW have to learn that this other kind of wire is not a normal LabVIEW dependency wire, but it is a data flow wire. It's flowing data through the pipe from one loop to another. So the channel endpoints in the diagram here, if you can see my mouse, Here's the write endpoint. Here's the read endpoint for this channel. And the endpoints are just subVI calls for writing and reading values to and from the channel. There are multiple kinds of channels for different communication strategies. The most common are stream, which is like a point-to-point FIFO or queue, tag, which is similar to a constrained global, and messenger, which has aspects of both. You can have multiple readers and writers. It has queue-like semantics. All of these channels are strongly typed, just like regular LabVIEW wires. And you don't drop a channel endpoint from a palette. You create it by popping up on a terminal. And you can find out a lot more about channels by taking a look at the examples in the example folder. They show different use cases, different examples for different styles of channels, as well as design patterns, such as the channel message handler pattern, which I modeled on the queue message handler. And that's what I'm illustrating at the bottom of the slide here. There's a UI loop over here with an event structure, and it sends commands along the messenger channel to the message handling loop. And this loop processes the messages and does whatever actions it's going to do, DAC acquisitions and whatnot, and sends status information back to a display loop, which is part of the UI. So this is a pattern that I think is pretty universal, and it's kind of what the queued message handler was doing. I'm doing it with channels in this case, and I think it might be a little bit easier to see what's actually going on. One interesting thing that I want to point out is that some channels have a sideband communication. This input here to the stream write endpoint tells us, it is used to tell the stream that this is the last value that's being queued. And that can be used to stop this loop. So this sideband communication allows synchronized communication from writer to reader, such that you don't have race conditions when you're trying to start up or shut down operations. And I think that's something that can get tricky if you're trying to implement this at a lower level yourself. But one of the biggest advantages of channels is that you can actually put a probe on the channel. And when you put a probe on there, you can see all the data that's in the channel, and you also have the ability to single step, meaning that you can advance to the next read or write operation on the channel and halt execution at that point to inspect what's there. So I think the debugging possibilities with channels will make application development so much easier and faster. My recommendation is that if you find yourself building an application with concurrent loops, use channels and simplify your life. So one other quick example is, this is also in the examples folder, stream processing, similar to what you might do with Unix pipes. So all of these VIs are running concurrently, and they're transferring data across streams. So here's one stream of strings, here's another stream of strings, another, and so on. And the first VI opens up a file, reads it out line at a time, and produces a stream of strings, one per line. The second one filters those strings, that stream of strings, and passes through only the ones that satisfy a certain pattern. So this is like grep on the Unix command line. This one reads in a stream of strings and breaks each string up into individual words. So it writes out many more strings on the output than it reads on the input, basically the number of words per line, and so on. So the main point of this is that if you have a collection of these stream processing VIs, you can string them together and pretty easily construct a variety of stream processing applications. You know, similar to, in this case, the way we would do pipes on a Unix command line. Okay, so now I want to tell you a little bit about the target structure. This is, you know, if channels could simplify the representation, communicating between concurrent loops, concurrent actors, today running on the same machine, but what if you want these actors running on different machines? So that's where this target structure abstraction comes in. So this is still a research experiment, so don't take the UI or the graphics here too literally. It's still early stages of experimentation. But the idea is that this is going to allow the representation of distributed applications using a single canvas. So what do we do today to send data from a loop on RT to a loop on the FPGA? We have to create two VIs, one on each device, using three windows, add project window here, allocating a special resource to do the communication and so on. But in the vision of the target structure, we'll be able to do this all in one diagram. A single canvas with a simple visible connection. I have a channel that spans from my host or my RT diagram to my FPGA diagram. And it ought to be this simple to construct. So at the syntactic level, the target structure is similar to other structures in LabVIEW. However, the diagram inside the target structure is compiled for, deployed to, and run on a different machine, in this case, the FPGA. So what kind of challenges do we have in trying to make the target structure reality? At the high level, the concept seems simple enough, but there are these challenges. For one thing, compiling and deploying, we actually know how to do that. The project tree does that. But can we do that automatically behind the scenes? And so in fact, a lot of the experimentation we're doing is using the project tree, but trying to keep it in the background and automate the construction and navigation project tree. A channel that crosses a target boundary needs to use some kind of hardware. The hardware and resources and driver interfaces exist. We have a myriad of ways to do that, and they're all available in the project tree again. But can we automate and orchestrate this automatically so that it's not something where the user has to deal with all the details and get all of that correct? So another question we have is it useful to have a target structure within another structure in LabVIEW, inside of a loop or a case or a subVI, or inside another target structure? And what would it mean? Actually, the first three of these bullet points here, we've been experimenting with and prototyping, and we've got some good proofs of concept, and I think we're pretty confident that we can make this work and work well. That obviously be a lot of work to get it productized, but we're pretty confident that we could do that. The last two are still very much in the research stage. How could we represent disconnecting and reconnecting to a remote target? And how would we implement debugging and probing, single stepping, and so on? So those are still early stage research topics. So one of the folks on our team, Newton Peterson, has been focusing on the FPGA cases. He's been experimenting with Elvis 3 and CRIO and PXI And he's prototyped target crossing channels that use DMA FIFOs and FPGA registers. And his approach is to script a project tree to leverage its functionality, but to hide the complexity. And that seems like a really good strategy for us to follow. For the time being, there's a pop-up on the target structure to compile it, since it takes a while for the FPGA to compile. Hitting the run button starts the host application, which deploys the FPGA bit file, starts it, and also coordinates the establishment of the communication channel between the host and the target. I've been focusing, on the other hand, on looking at the networked CPU case. And so I'm going to illustrate that with this little example that I created. That's a simple stream processing example again, where the loop on the left here generates a letter each 2 seconds. And then the first loop appends a phrase, second loop appends another phrase, third loop displays the result. And what I want to do is have this distributed. So this, I'm going to show you a video here of a screen capture on my iMac. So the background window here is actually showing a Windows virtual machine running in the Amazon cloud that I've remote desktop into from my Mac. And in the foreground is a VI that's running on my iMac. And I'm going to introduce target structures in here to distribute the execution of this. So we'll see if the video plays. Okay. So first thing I want to do is drop a target structure around the second loop and give it the address of a different iMac that I have sitting next to the first one. And then I'm going to select this update instance in order to get the code ready to deploy. That should be automatic in the future. I'm also going to put a target structure around the second loop and give it the IP address of the virtual machine up here. And so again, update that to make it ready to go. Now when I start it running, I'm going to end up deploying the VIs so that they can be run. You can see it start running on the virtual machine in the background, and then the display starts catching up. Because while it was starting up, there was data being enqueued in the in this stream over here, and then when this started up and this started up, it was able to process, and the display, since it's displaying every 1 second, it will catch up. So the other interesting thing is I'm able to hit the stop button over here, and that propagates through and stops my distributed pieces as well as my display loop. So it all behaves as expected. So the point is that if we can get this target structure operational, it ought to make distributed applications much simpler to create. And in fact, in this case, I have parts running on my Macintosh and parts running on Windows machine, and it all behaved just properly. Okay, so here's another example that I've played with to see what it means to have a target structure inside of the LabVIEW structures. So here I've got a parallel for loop that creates two instances of my acquire, analyze, present example. So I have an acquire loop, a presentation loop, and an analyze loop that's in the SubVI. So each subVI contains an instance of a loop running on a target. And the channels in and out are two sets of TCP/IP connections that allow me to connect from my host computer to my other computer. And I've actually got both instances running on the same processor, as two independent instances running on the same processor, but I could actually distribute them to different CPUs by wiring in the target address as opposed to specifying it statically. But I only had one machine to show it. Okay, so I hope I've convinced you that channels are already here and you should be using them, and that target structures are still in research, but hold great promise for reducing the artificial complexity of building distributed applications. And I think the combination will enable you to be more effective building even more complex applications in the future. I should also point out that I'm using G to do this development and experimentation because of its flexibility and the rapid development I can do with it. A channel is defined by a library of VIs. So it makes it easier and faster to develop, easier to debug, and it's extensible by us as well as by knowledgeable alliance members. You can find the all the channels that are available on your system in resource channels folder. So far, we've similarly been able to define the target behavior, or most of the target behavior, in terms of a library of VIs. And my long-term goal is to make targeting a user-extensible feature so that you can create the VIs that define how to support new targets. So now I want to switch gears and talk about another channel that I've been working on that offers some interesting possibilities for representing more complex applications. So I was inspired by an application that one of our alliance members made that he was using channels, but it was more, it was trickier than I expected. And looking at his particular application, it struck me that I could perhaps define a more complex channel that would make his application simpler. So I've been experimenting with this multiplexed messenger channel, and it actually represents multiple messenger subchannels on a single wire. So it has the usual read and write endpoints with all the full complement of optional inputs and outputs. But what makes this channel particularly special is the subchannel index. So different writers and readers can dynamically choose which subchannel they wish to communicate on. And where might this be useful? So here's an example, simple example I built. I call it a Manager-Minion Example. There's a manager VI that controls 8 concurrent station VIs. And you'll pardon my primitive UI here on the main VI, but that's not the point of the example. So imagine a much nicer UI, if you will. So the LEDs here are showing the status of each station, whether it's off or active, pause, error, or it's finished, it's exited. The operator can select a channel with one of the buttons up here, then select a command with this pull down, and then hit this button to send the command. So what does this look like? Well, the diagram has the usual familiar UI event loop, event structure, and an event loop here, and then a status display over here, back on the host. And then these parallel stations. And here I'm running 8 stations in parallel. So the connection from the host to the stations is using a multiplexed messenger channel. And that allows the manager here to talk specifically to a particular station. And that station, each of these parallel instances is given its unique station ID. And the results or the responses from the stations are all merged back into a single messenger channel, but as part of the message coming back is a station index, and so that allows the display loop to know which station's reply that was. Yeah, okay, I just said that, sorry. So here's the code for the station VI, and don't worry too much about the code. I designed this using the state diagram editor, and I just pasted a picture of the state diagram so you can understand the different states of that the station goes through. So basically, I continue processing, doing 10 millisecond incremental processing while I'm in the active state, and then I exit the active state if I see an error, or if I'm told to pause, or told to stop, or told to exit. Yeah, so that's, so the main thing to notice here is that the station is reading from its assigned sub channel on this messenger channel, multiplex messenger channel, and it's using the station number in its reply message back so that the manager can see who it came from. So here's another video that shows this in operation. I started running, and it starts up all 8 parallel stations, and then I can start station 7 and 2 and 6 and 0, and I'll go back and pause station 2, and I can stop station 0, and then I can go over to exit 7 and say, I need to exit that one because that station is broken or not being used. I can pick some other ones to start, 5 and 4. I go back and I can resume station 2, and you can see that it goes back to processing. Station 6 detects an error, and I can go back and reset it and start it again, and pause, and finally just exit all stations, end of the example. So the takeaway here is that with that single multiplex messenger channel, I can very conveniently talk to a bunch of parallel stations. Eventually, of course, it'd be wonderful if I could have a target structure in each one of those stations and be having them deployed to individual machines. That's still in the works. Okay, so while I was experimenting with this multiplex messenger channel, I realized I could use it to model a bi-directional channel. And so I was thinking initially, I could imagine a policy where the manager would send a message to a minion on channel 2n and receive a reply on channel 2n+1. And I mean, a policy like that could work, but it's a little bit awkward. It seems like it'd be impossible to enforce and error prone if someone accidentally wrote on the wrong subchannel. And so I realized I could actually make it simpler and more secure by adding 2 more pairs of otherwise identical endpoints. So one set is used for the manager to send commands and the other for the minion to send replies. Instead of using indices, this pair of subchannels, one in each direction, is identified by a GUID. So how might this be useful? So here's an application with a dynamic number of clients, a server, and a dynamic number of workers, 1 per client. So this example, again, has a trivial UI, and I'm just using this to set it up. I can imagine a much more interesting situation for this to be working. But in this example, I have a button. Every time I hit a button, it creates a client. And the client sends a message to the server. The server spins up a worker, which then communicates with the client. And the 2 of them communicate privately until I finish. So here's the diagram. The client, every time I hit the new button, I spin up a new client, which sends a message to the server, and the server then spins up a worker, an asynchronous worker, and the worker and the client communicate on their private channel, private bi-directional channel that is defined by this GUID. So the client initiates the request for service by sending its GUID to the server, and the server launches a worker and then provides this bi-directional secure channel between the client and the worker. So here's the UIs that you'll see in my next example showing this. The client has a simple UI again, and I could imagine, and it's got buttons on here that I'm controlling interactively, but I would imagine this is done automatically and programmatically in a real application. Well, okay, so the worker, nothing to say about that. The worker UI is basically just for debugging purposes, but you can see it in the example. So here, when I start this example, if I launch a new client, the server spawns a new worker, and the worker and the client communicate, and I can control the different clients and see how they're communicating with their workers. And when a failure is reported on one client, I can still spawn other clients. I can exit clients, whether they succeeded or failed. And when the client exits, it sends an exit message to the worker, which exits, and the client exits. And all the while, I can be operating the clients independently, and they're communicating with their workers. And it's all happening, all represented on this single multiplexed messenger channel. To take a look at the code, again, you don't have to worry about the details, but notice that the client is very similar to the typical event loop and the event structure and a UI loop and a display structure. It's just that the commands are going out and the responses are coming back on this same bi-directional channel. And so it's a similar pattern, but maybe being able to be represented a little bit more compactly by having a single bi-directional channel. So that channel is identified by a private GUID per client. And so this GUID is sent to the server, and when it's sent to the server, then this channel becomes active using that GUID to receive a response or send a command. And here's the worker diagram. Again, it's similar to the processing loop that we've seen before in the other examples. Again, never mind the details, but notice that the command is being received on the channel that specified by the GUID that the worker was given when it was started. The server gave the GUID to the worker is using that GUID to receive commands, and it's also using that to send responses. In this case, it's sending status responses continually until it finishes and then is told to exit. So let me finish up with one item that's just kind of pure fantasy at this point. This design pattern up here is a compact way to show multiple asynchronous clients talking to multiple asynchronous workers. And that's, I think it's a useful abstraction, but it doesn't show enough of the dynamic behavior in the diagram. And so I'm still trying to hallucinate what a good way to represent a dynamic diagram that can show the connections as they come and go. So in a sense, this design pattern up here is a generator of a dynamic diagram. So this is a little kind of a vision of what an execution highlighting of a dynamic diagram might look like, at least at this stage of my thinking. In the beginning, you have the server and it's sitting there idle. Along comes a client, messages the server, gets a worker, communicates with the worker. Another client comes along, third client comes along, and that third worker is set up with its communication channel. Second worker finishes, first worker finishes, the client goes away, and then finally the last one finishes, and we're back to an idle situation with the server sitting there waiting for a client to come along. So, is something like this possible? I have no idea, but it seems like that's the kind of thing you'd like to have available while you're debugging or watching your dynamic system execute. So I presented a lot here very quickly, but I think the main points you should take away are that channels today can simplify your life if you're making concurrent applications, so please use them. And stay tuned for more progress on target structures. I think they will hold out a lot of promise for simplifying things in the future. Thank you.
So hello, thank you, Jeff. That was an amazing presentation. It gives a good insight in the future features that will be shipped with LabVIEW, and I'm really excited. So we have a few questions in chat, and the first obvious one is, of course, when will this be shipped? When can we play with it? When can we start developing with it?
Yeah, that's always a tough question. So the last thing I talked about, the messenger channel, actually, I have it. It's just a library of VIs. I can zip it up and send it out to anybody who's interested in it. It's probably workable and usable today, but it's the kind of thing that I'd love to have more feedback on to make sure that I get it all working smoothly before it's actually an official part of the product.
Mm-hmm. So maybe you can set it to us, and we post it here on the YouTube video and the forum, so people can download it and maybe give you feedback from.
Yeah,
okay.
That'd be great. As far as the target structure goes, we continue to experiment, and I guess I'm of the opinion that we're getting pretty close to having sort of the first tranche of usable capability that would help in many of the more static applications, say host and RT, or host and Raspberry Pi, or host and RT, maybe RT and FPGA.
FPGA, yeah.
The ones with the FPGA are a little bit trickier, obviously, and have a little bit more machinery that has to be really vetted out. And so, but maybe the version for doing between processors, like to RT and to Raspberry Pi and so on, is something that we could get out in experimental form sooner rather than later. Because again, I feel like I could try to evolve things more myself with experimenting, but I'm not going to run into the same kinds of things that people doing real applications are going to run into. And so if there are a few brave souls who are willing to help me experiment with some of this, that might be something we could do before too long.
Sounds good, yes. Another question that we have is, what possibilities will there be for getting target structures to communicate with other already running on the target? It's with other target structures already running on the target.
So this is something I haven't done a lot of thinking about yet, but in the examples, you notice that the way we communicate between one processor and a target is through channels. And so we can send a stream of data or a tag across it. And so to the extent that we could have an interface on the target written in another language or another system that could do the protocol necessary for communicating over a stream or a tag or something, then it ought to work just fine. But I'm sure there's lots of gotchas, and we'll probably end up with a lot of different little issues to address. So in the future, I think this is something we obviously want to do, but it's not where our primary focus is off the bat.
At the moment, yeah, sure. Yeah, of course. So I'm looking at the people who are monitoring the chat. There are no more questions at the moment. So if somebody has a question, please ask it now. Now is the time. Yes.
Yeah, I realize a lot of the stuff I went through really fast, and a lot of it might be quite new to folks. So
yes, some people will see that the first time, and the hard thing that I have is it lets a little bit loose from the data flow that you know from LabVIEW. So some block diagrams are really hard to comprehend at first sight, because you are not you do not look at block diagrams that way yet. So it's a little bit practice, yeah.
Yes, that's very very good observation. In fact, we did an experiment a couple of years ago in Yerevan, Armenia. We took some students who were just learning LabVIEW, and we taught them about channels in the LabVIEW 1 class. And they got it, they understood it, they were able to develop their little example applications just fine, no problem. We also took a group of third-year college students who had already been using LabVIEW for 2 years, and taught them about channels. And they actually took a little longer to understand, because they had internalized the notion that if you connect something with a wire on LabVIEW, It means that data is flowing and that the second node is dependent on the first node finishing before it can start.
Yes.
And that's true for the regular LabVIEW wires, but the channel wire, which we purposely draw differently, although maybe it's still a subtle enough difference that it takes a little bit of experience to get comfortable with it. But that one actually means this is a pipe. It's still data flow, and it's still by value, but it's happening not after this first loop finishes, sending an array of data to the second loop. It's happening a point at a time through this pipe. And so it's doing something that we already do in our applications. We do this with a queue, right? You have a allocated queue, and then you pass the reference to the writer and the reader, and this enqueues, this dequeues, and we have this magical property of something I write over here appears over here. There's a flow of data, but you don't actually see it. So from my perspective, what we're doing with channel is actually showing the path of the data and showing that here's the reader, here's the writer. But you do have to learn that this channel connection is not the same as a regular LabVIEW wire connection. A LabVIEW wire implies scheduling dependency, whereas a channel wire implies concurrency.
Yeah. The most the best benefit I see for channel wires, or that I saw at channel wires for using them, is that when you get to use other people's code, other programmers' code, and they're using named queues, it's not immediately clear where those queues are enqueued and dequeued. You have to basically scan the whole project library to find out if there are, and that's a problem. But with channels, you can follow to where the data is used, and that's that makes everything more visible.
Yeah, and that's exactly right. And that, to me, that's one of the strengths of LabVIEW, in that you see where data is generated and where it's used. And in typical text-based programming languages, you're using the name of the variable. And so to be sure that there isn't someplace else that that variable is being used or being reset or whatever, you have to scan your code or use some other tools. But if you have a wire representing the transfer of the data, you can tell at a glance, well, here's where it's being generated, here's where it's being consumed. So I think the same thing happens with a queue now. I can represent the queue with a wire, and I can see the source and the sink, but I just have to remember that, okay, this wire means that things are flowing at runtime between these two loops, and this other wire means that first this loop finishes and then this one starts.
Exactly. Yeah. We have another question. Would it be possible to configure target structures programmatically?
So I can imagine that you might want to script a target structure and script the address of the target that you want, so that you could automatically configure a system based on some information about the targets that you have. And so on. So we do have the ability to script a target structure. It's even more primitive than the target structure itself is, but that's certainly being thought of. We want to be able to do that.
Okay, that sounds good. But because I think a lot of plugin architectures will be very useful.
Right.
Yes. So I'm looking at the chat again. Are there some more questions, guys? Round up? No, there are no questions.
Okay.
That's bad.
If you get any in the future and you want to forward them to me, certainly know how to reach me by email, and I'll be happy to answer any additional questions.
Yes. So for all the presentations, that's if you send an email to Dutlug or post them on the community thread, I will make sure that it is forwarded to the correct presenters and you will get an answer. Yes. Yes, and hopefully a lot of people will start experimenting with these structures and the channels and give you some feedback. Okay.
Wonderful.
Yeah. So Jeff, thank you very much again.
Thank you.
I think it's really appreciated, and hopefully till next time.
All right. Stay healthy.
Bye-bye. Stay healthy. Yes.